Welcome back to Learning with the Fosters, where today's classroom is Playa La Mela, again in Cabo Rojo, Puerto Rico. A beautiful beach, a great place to come. We'll continue or resume our discussion regarding real numbers and the real number line and intervals shortly. But today we're going to take a slight step back, a little excursus, if you will, into some fundamentals that are quite important as we move forward with our discussion. If you recall, we're taking our time anyway reviewing basic fundamental concepts before we actually get into the algebra and trigonometry that dominate this course. So today we're going to take a step back and look at order of operations and exponential notation. Well, order of operations. You know, in a very important sense, mathematics is a language in some ways. Now, it's different than our verbal languages spoken around the world throughout time, but it's similar as well. And we won't get too philosophical or technical or use linguistic terms too precisely, but it'll help, I think, a little bit to kind of draw some similarities and differences as we talk about order of operations. If you think about languages, they're expressing an idea or expressing a description or whatever. We could describe this blue house over here using language. Well, in some sense, language is convention imposed by humanity as to how we communicate. Or in other words, there's certain rules to the language to be able to make it useful. And we have to be familiar with those rules to be able to communicate that language. Now with spoken languages, there's the alphabet, the phonetics that are behind that. And if we go back farther in time, there's kind of symbols representing words. But you have to become familiar with the alphabet. Those make a phonetic sound. And then you have to be able to understand what the lexical meanings of those words are. And then, but to really say anything, you have to be familiar with the syntax or the basic grammar, how one constructs certain things. And there is no, necessarily set way to do that. In fact, our languages that are still spoken today are quite different. Just for but a few examples. Reading direction. In English and Spanish and a whole host of other languages, we read from left to right, starting in this direction and moving this direction. Well, other languages, for example, Hebrew and Arabic and other languages, move from right to left. We could construct a language where we move bottom to top, or top to bottom, or diagonal, or all sorts of ways. But these are constructs that we create to be able to communicate what it is our language is attempting to speak. But we have to be familiar with those rules to be able to speak that language. Another item is, if we were describing this blue house over here, even the difference between English and Spanish, where the adjective blue is modifying the noun house. In English, we place that adjective before the noun. In Spanish, most of the time, correct me if I'm wrong, D.S. Foster, El Profe, the adjective follows. It would be casa, which is house, azul, which is the color, blue. So in English, if we transliterated that, it would be house blue. So you can see how languages in Spanish and English are very similar in some respects, how there's different orders, there's different rules. Well, math is no exception in that regard. There are rules when we suddenly talk about operations with numbers. If one thinks of numbers, we've been looking at real numbers, we'll be looking at their properties shortly. Those we could kind of compare to small bits of information in spoken language, whether we break that into phonetic letters or perhaps words. But when we string those together in any sufficiently complex order, we need to understand the syntax or the grammar of the language we're speaking. In this case, mathematics. In this case, the pre-calculus type mathematics. Now, with that being said, of course, one could think of constructing mathematics using slightly different syntax or different rules and coming up with different consistent sentences and systems. But for what we're dealing with today, we're kind of reviewing some of the basic grammar of operations. Or in other words, these numbers we've been looking at, how do they interact with each other using some types of operations: addition, subtraction, multiplication, and division. Well, let's take this example for example. Let's evaluate this expression. We have 4 minus 2 times 3 plus 1. Well, what's the answer? All of these individual operations and numbers are sufficiently easy for us, I think, at this point in our mathematical career. So what is our answer? Well, let's take 4 minus 2, which is 2. I'm just bringing my work down, multiplied by 3 plus 1. 2 times 3 is 6. Plus 1. 6 plus 1 is 7. So we get 7, moving from left to right. So let's put left to right, we get 7. Well, let's try something else. Let's move from right to left. 3 plus 1, or 1 plus 3 is 4. 4 times 2 is 8. 4 minus 8 is negative 4. That's a totally different number than we got just by switching the direction that we go. Well, what if we did something else? What if we have kind of a nice even pair of operations in a sense? Well, odd total, but we can let's just work from the ends. Let's take these two and then multiply the results. So 4 minus 2 is 2, times 3 plus 1 is 4, 2 times 4 is 8. And we get another number. I think that's sufficient to demonstrate that we need some sort of grammar or some sort of syntax or order in order to perform even a basic expression like this. So in math, what we have are a list of the order of operations in how we look at mathematical expressions. In a sense, how these expressions are written allows us to, following those rules, evaluate them correctly. So even though languages, written language, verbal languages, mathematical language, may express or may have different rules to follow, they're all capable of expressing a statement, such as the blue house. We may read from different directions, we may place different orders and say things like adjectives and nouns and all sorts of hosts of other rules, but they're all saying, or they're all capable of describing those scenarios. Well, math, we want to describe something useful as well. So we need some sort of order or steps of operations to proceed with. So let's work through some basic ones. The first thing we do are we deal with grouping symbols. Well, what are grouping symbols? First thing we'll look at are fraction bars. For example, if you have a fraction, a plus b plus c over b minus e. There's an expression. Here's the fraction bar. What do our order of operations tell us to do, or what is the order that our grammar, if you will, works with? We work separately above and below the bar. So we'll deal with this expression and this expression separately. This one on top, this one on bottom, but we'll simplify this, and then look at the simplified version of this over the simplified version of that. So a fraction bar is a grouping symbol, even if we're not used to thinking of it that way. Because remember, a fraction, one thing it's saying is divided by. Numerator divided by the denominator. So if you see a fraction bar, that's the first thing to deal with. We're going to work separately top and bottom of the bar, or above and below the bar is what I should say. The next thing we look at are grouping symbols like, these are just a few examples, parentheses, brackets, and these we'll deal with very shortly in our course, absolute value. You'd have something like a, b, 7, negative 5. Don't worry if you don't know what that is yet, we'll deal with that shortly. But these are grouping symbols. Now these can be embedded. You can have parentheses within brackets and an absolute value embedded in between those. We'll look at plenty of examples where you'll see stuff like that. So when that happens, you start with the innermost set and work outward. So you start with parentheses. If there are embedded parentheses, you start with the innermost one and work your way outward. After you're done dealing with these grouping symbols, then you simplify exponents and roots. We'll look at some basic exponential notation today. Again, I'm sure you're familiar with it. We'll spend some time with exponents in the future, but today we'll just remind us or be introduced to some basic exponential notation. We'll ignore roots for today. Again, we'll be dealing with those throughout the course, but we'll get to those later. So after you simplify exponents and roots, Then you deal with the operations multiplication or division in order. Well, what direction here? We work left to right. After we're done with the multiplication and the division, we handle the additions or the subtractions, again in order, moving from left to right. So let's review one more time before we look at some examples. The order or the steps of operations that we look at. 1, grouping symbols. Fraction bar works separately above and below the bar. Things like parentheses, brackets, absolute values, and again, those can be embedded within each other. Start with the innermost set and work outward. Then we simplify exponents and roots. Then we multiply or divide in order, moving from left to right. Then, last but not least, we add and subtract in order, again moving from left to right. So let's consider some examples. So here we have the expression, parentheses 5 plus 3, parentheses divided by, parentheses 10 minus, parentheses 6 minus 4, parentheses times 3, parentheses plus 7. Let's evaluate this. Now you can see already the importance of having some sort of order. I mean, there's quite a number of ways one could tackle this without any type of order. And as we saw from just that small example at the beginning of the lesson, that we would probably get some quite different answers. So let's follow our steps, our order of operations with this example. First thing to look for are grouping symbols. Is there a fraction bar? Well, no, not in this one. So let's move on to symbols like parentheses, brackets, and absolute values. We won't be dealing with absolute values today, so we'll just ignore those. Well, yeah, we've got some parentheses. We've got a group here, we've got a group here, and a group in here. Where do we begin? Right, the innermost one. So we'll begin with this parenthesis. See how these are embedded. There's a parenthesis here. So we're dealing with this section. We're first going to begin with these parentheses, because they are our innermost parentheses. So I'll encourage you when you're working through these to just do one step at a time, because it's easy to make a mistake if you're doing multiple steps at a time. So we're just going to work with one, and I'll show you how I keep track of this information. There's a variety of ways to do it, but this has worked well for me. The portion I'm working with, I like to see what I'm doing, where my answers come from, because inevitably you'll make a mistake and you want to be able to go back and check to see each step where you may have erred. So this is the step we're going to do first. Remember, we are not going to start just left from right and work. We're following our order of operations. Our first step is our innermost parentheses with this particular problem. So we'll evaluate this simple expression, this operation 6 minus 4, which is 2. Now what we want to do is bring everything else down, and we'll notice as our expression slowly gets simplified. So the way I do it is I keep everything straight as it was. So directly down. Bring all this information down, and again, when you get used to these, you may say, hey, I'm just going to do this step right now. I would encourage you to take it slow, even as you progress in your math career. I still do one step at a time, all of the time, because I'm less prone to make an error. Okay, so we have essentially the same original expression with the simplification of this parenthesis subtraction operation. Well, what do? No fraction bar, we're still dealing with parentheses. So we're going to start left to right. Here's our first set of parentheses since we took care of our innermost one. So we'll deal with this. 5 plus 3 is 8. And again, we're going to bring everything down. All right, next step, we still have parentheses, so we need to take care of that. So we're dealing with this section. All right, but we have multiple operations. So what do? Do we start with the 10 minus 2, or do we start with the 2 times 3? Well, when we get done with parentheses, we simplify exponents and roots. There are none of those. Then we do multiplication and division, working from left to right. So we have multiplication, so that supersedes in priority the subtraction. So even though the 2 times 3 is to the right of the 10 minus 2, we do our multiplications and division before we do our additions and subtractions. So our next step, we take this 2 times 3, which is 6. Now we bring everything down. Okay, we still have parentheses, so we will deal with that now. Head minus 6. 4. Again, bring everything down, and I like to keep them spaced the best I can. Even though it generates some large gaps, it again helps me not make errors. And if I need to go back and check my work, I can see more clearly where the moves I've already made. All right, hey, this is looking simpler already, isn't it? So we're moving from left to right. There are no more grouping symbols. So the next thing we do are exponents or roots. There are no exponents or roots. The next thing we look for are division or multiplication going in order. Well, we have a division right here. So 8 divided by 4 is our next operation. 8 divided by 4, of course, is 2. Bring everything else down. And now we are left with the singular operation. 2 plus 7 equals 9. And 9 is the correct answer for that expression. Let's look at another one. All right, for this particular example, we have a fraction bar, don't we? We have the expression 4 multiplied by 3 minus 2 in parentheses over 6 plus 9 times 2 minus 10. Now again, just a quick review. This means multiplication. There's a variety of ways to denote multiplication. Just to list some of the more common ones, we could say A times B for A multiplied by B. We could say A dot B, saying the same thing. We could say A B with parentheses. We could say A in parentheses times B. Whenever there's a parenthesis like this, these two, there's an implicit multiplication action going on. And again, I'm sure all of this is review, so we're kind of moving through without spending too much time on it. But I know these are things that we may forget, or it may have been a while since we've actually used them, so I think it's useful to refresh on them. But if you need a little more explanation on these, I'd encourage you to consult maybe a pre-algebra type textbook or something like that. But just a little reminder of some different ways that we can denote multiplication. So this is saying 4 times this quantity. This is saying 9 times 2. All right, this one looks kind of fun. So first thing we look for are fraction bars, which we have right here. So what are we going to do? We are going to work separately above and below the bar. So let's first deal with this top expression. 4 times 3 minus 2. Let's deal with this first, and then this will become our new numerator. Then we'll deal with the bottom, simplify that, evaluate that, and that will become our new denominator. So, just dealing with this portion, the next thing we look for are grouping symbols such as parentheses, which we have here. 3 minus 2 is 1. 4. Now, something you'll notice here. If we don't bring down these parentheses, we have a really odd statement. It looks like we have 41. So it's important to bring down parentheses until they're not needed anymore. We'll talk about some of the properties of real numbers involving parentheses and how they operate in a few lessons. But for now, just remember that. So even though technically we don't need parentheses because there's no other operation, we really still do, to be clear, because otherwise it would just be 4 times 1. Or excuse me, it would be 41. There's no operational symbol. So 4 times 1 is, of course, 4. So this is our, what? Our new numerator. So 4 we've simplified this. Now let's simplify our denominator. So let's rewrite that. 6 plus 9 times 2 minus 10. All right, there are no grouping symbols, so when we do multiplication and division, do we have any of those? Addition, multiplication, right there. So 9 times 2 is 18. Bring everything else down. Now we just have addition and subtraction left. That's the last thing we have to worry about. So which one do we do first? Well, we move from left to right. So 6 plus 18, 24, minus 10. One more operation to do. 24 minus 10 is 14. So this is our new denominator. Okay. Are we done? Well, we can simplify, right? This is a fraction. This is a division problem. We can simplify these. We can divide both the numerator and the denominator by 2. We're left with 2/7, or 2 over 7, a rational number. We simplify this expression. Let's consider one more example. First thing to do, is there a fraction bar? No. Are there grouping symbols? Yes, parentheses. So we're working within these parentheses first. Are there exponents or roots to simplify? No. Are there multiplication or division? Yes. So we'll do that. 6 times 3 is 18. Bring everything else down. All right. We're still working within these parentheses. 2 plus 18. 20. Bring everything else down. Remember, keep these parentheses. All right, so there are no more grouping symbols. Remember, there's just a 20 between these. So what do we do next? Multiplication and division in order from left to right. So we basically have this division, right? But wait a minute, what is this negative sign here? What do we do with that? Well, this is negative 20. We can always think of, and we'll explore some of these properties more in the future, but really there's an implicit 1 right here. Negative 1 times 20. A negative times a positive is a negative. So a negative 20, so really we're doing this operation first. Negative 20 divided by 10. All right, negative 20 divided by 10. A negative divided by a positive is a negative. And again, if it's been a while since you've kind of gone over some of those rules, I'd encourage you to kind of do some research on that. Again, we won't explain why those are at this point, but well, let's just quickly go over some. If you multiply or divide, a positive times a positive is a positive, positive times a negative, or negative times a positive is a negative, and two negatives multiplied or divided together are a positive. So a negative divided by a positive is a negative. So negative 20 divided by 10 is negative 2. And there is our answer. Okay, while we're reviewing order of operations, I thought it might be a good idea to review basic exponential notation as well. That way we can practice some more or we can add exponents into our order of operations practice. And also it's something that, again, we're probably familiar with, but it may have been a little while since we've looked at it. And since that's what we're devoting this whole lesson to anyway, is review of these type of things, let's look at some basic exponential notation. And remember, look forward to in the future, not too far off, we'll be looking at exponents in a little bit more detail, a little bit more depth. They're very important items. So exponential notation, consider this example. 4 times 4 times 4 times 4 times 4 times 4. Whew, well, that's a product. That gets a little bit old writing, right? So what we can say, or we denote this as 4 with a little 6 above it. What this is saying is there's 6 factors of 4 in the product. There's 6 factors of 4, 1, 2, 3, 4, 5, 6 in the product. So we write that as 4 with a little 6 on top. This is exponential notation. Isn't that a lot easier? Let's look at this one. we have negative 3 times itself, 1, 2, 3, 4, 5. We can write that as negative 3 with a little 5 on top of it. Again, we have 5 factors of negative 3 in the product. But we can generalize this. Let's look at any a to any n, or any a with a little n on top of it. That is equal to, just like we've been noticing up here, the little numbers tell us how many factors we have, right? So n factors of, well, whatever the a is. Up here, the big number was 4, so we have 6 factors of 4. Here we had negative 3, we have 5 factors of negative 3. Or in other words, 6 4s multiplied together, 5 negative 3s multiplied together, or in other words, n a's multiplied together. So a to the n is representing a product of n factors of a. Or in other words, a multiplied by itself n times. That's what we're talking about with exponents. Now the n, let's get a little bit more precise in our terminology. The n is the exponent, the little number I keep referring to up top. That's not a little number, it's an exponent. Again, that tells us how many factors of the base, a is the base, are present in the product. The little n, the little number, is the exponent. The big number, the a, is the base. So when we speak of exponents now, we can be more precise. Instead of saying little number and big number, we can say the exponent and the base. The exponent tells us the number of factors of the base in the product. So a to the n is the exponential or power. We read this as a to the nth power, or simply a to the n. Let's look at an example. All right. Let's evaluate some of these exponents. Marius is really loving these. All right. 2 to the 4th is how we would read it. What is this saying? Our base is 2, our exponent is 4, so we are taking 4 factors of 2. So let's write this out as, here is the base, this is the factor. How many times are we going, how many 2's are we going to multiply for the product? Well, 4. So 1, 2, 3, 4. The exponent tells us how many of the base we're multiplying together. Well, let's evaluate this using our order of operations. All multiplication, that makes it easy. We're simplifying this. So working from left to right, 2 times 2 is 4. Bring everything else down. 4 times 2, 8. Times 2, 16. So 2 to the 4th is equal to 2 times 2 times 2 times 2, which is equal to 16. Let's look at this one. 9 to the 2nd, or this is commonly referred to as 9 squared, because when we find the area of a square, we take all the lengths are the same, so we take the same number, let's call it w times w, so w times w is w to the 2nd, or w squared. So we can write this as our base. How many times? Our exponent is 2. So 9 times 9. This is 9 to the 3rd. We would take another factor of 9. 9 times 9 is 81. Now notice, this is a very different answer than, we're not saying 9 times 2, are we? No, we're taking 9 times 9 with 2 factors. The product is 2 factors of 9. So 9 to the 2nd is equal to 9 times 9, which is equal to 1. Let's look at this one, a negative. D.S. Foster really was having fun with this. So let's not panic. Let's just know what we've been doing. We have our base, and we have an exponent. So our exponent tells us how many factors of the base we're utilizing. So 3. So we're going to take negative 3 times negative 3, another time, times negative 3. Remember, This is an implicit multiplication symbol going on here. So let's simplify this. All multiplication, negative 3 times negative 3. A negative times a negative is a positive. 3 times 3 is 9. Bring down the last factor. Multiply that together. A negative times a positive is negative. So negative 27. So negative 3 to the third, or cubed, if you think of our example as squared, you can see how the cube comes in, is equal to negative 3 times negative 3 times negative 3, which is equal to negative 27. Now, let's use our refreshment on exponential notation and our refreshment on order of operations and put them together and have some fun with some things that we probably haven't had fun with for quite some time. But I promise, they're still just as fun now as they were back whenever we first learned these. Evaluate this expression. Order of operations, exponents at play. First thing we look for are fraction bars. We have one, so we're going to work above and below that separately. So let's first work on the top. We have 6 plus 5 squared minus 11. So 6 plus 5 to the second minus 11. Order of operations, there are no grouping symbols. But what do we have next? Exponents. So we are going to simplify this exponent. 5 squared. Let's just for at least this one, write that out. 5 times 5. Our base is 5. Our exponent is 2, so we're taking 2. Our product has 2 factors of 5. Let's bring everything else down. Five times 5 is 25. Now you can maybe see why we deal with exponents and roots first, being the operation behind them. Alright, now we're left with 6 plus 25 minus 11. No grouping symbols, no exponents, no roots, no multiplication or division. So addition and subtraction now, we work from left to right. The syntax of the math that we're using. So 6 plus 25. 6 plus 1, 31. Minus 11. Not too bad. Hey, that one kind of worked out nice. Good thing about creating these problems is you can make them work out sometimes. Negative 31 minus 11 is 20. Okay. So that's not the final answer though, is it? Remember, this is just the top portion. So let's move 20. Up to...
So that's supposed to be a negative?
Excuse me?
Is the 20 supposed to be a negative?
No, good question. We're subtracting 11, but we're subtracting 11 from 31.
Oh.
So 31 minus 11 is 20. But anytime you're doing subtraction or negative, it's always good to check. So thank you for clarifying that. We're asking for clarification on that. Yes. Thank you very much. Negatives cause more problems, other than probably my kids, our kids, and grandchildren. Negatives, I probably lost more hair over missing a negative, forgetting to write it, or just ignoring it than anything else. Negatives are very important to keep track of. Okay, so now let's simplify the denominator. So we have some grouping symbols, some exponents, some multiplication, and some subtraction. So first thing we do, grouping symbols. We're going to deal with this area first. So we're ignoring this for now. So looking inside of here, what do we do first? Exponents and roots before subtracting. So we'll take 2 times, or 2 to the third, excuse me. Let's write this. 9 minus 2 to the third, we will write as our base is 2. And how many factors of 2 do we have? 3. 2 times 2 times 2. Bring the rest down. Alright, let's simplify this. 2 times 2 is 4. Now I'm doing this longer than we typically do, especially 2 to the third. A lot of us have that memorized or can process that in our head fairly quickly, so you don't need to go through all these steps. but just to kind of show where it's coming from, I'm taking the liberty to do that right now. And I think it's always better to take extra time and show extra work than to simply assume that we should be able to do these things in our head. Math is something that uses a lot of paper. You're going to go through a lot of paper if you do math and if you do it properly. So, still working within these parentheses. 4 times 2 is 8. And this is a good one to memorize. 2 to the third is 8. Alright. Working within grouping symbols. Now, is this a grouping symbol? Well, yeah, it's parentheses, but everything inside it has already been done. It's simply a number at this point. So there's nothing to do within those parentheses. Here, there are. So 9 minus 8, 1 minus 4 times 3. Alright, we have parentheses but no longer grouping symbols because all the operations within inside of those have already been done. So we have 1 minus 4, remember an implicit multiplication. So what do we do first? Subtraction or multiplication? The multiplication, divisions and multiplications before the additions and subtraction. So we have 1, I'm going to drop the parentheses at this point. 4 times 3 is 12. Alright, one thing left to do. 1 minus 12 is what? Negative 11. So this is our new denominator. And we can't simplify this any farther, can we? So here is our simplified expression. So this is equal to this. The rational number 20 over negative 11. For this example, we're going to let Q equal 4, R equal negative 7, and S equal 2. Here's our expression. Let's evaluate. Negative 3 times S to the third plus the quantity 10 minus Q times R. Now when you're dealing with variables, when there's 2 variables or 3 variables or however many next to each other without any other operative symbols, there's again an implicit multiplication. We could just as easily put X, a dot, or parentheses. When you're dealing with variables and you see them strung together like that, it's multiplication. Alright, again, while we're reviewing some topics, I wanted to have a chance to look at one of my pet peeves when tutoring or teaching math. Of everything that causes errors, this has got to be within the top 3 that I've been experienced with when helping others get through their math solutions. We're going to be substituting these values in for the variables, right? Always use parentheses around substituted values to avoid errors. So what I mean by that is these variables we have a value for. So in order to simplify this, we are going to substitute in the values for these variables. So let's do that first thing. We have, and I'm going to do that in yellow, we have negative 3. Our S is 2. So this is not the way to do it. 3 times 2 to the third. That's technically correct, but for reasons that we'll even begin to see throughout these assignments, always when you substitute values, use parentheses. Parentheses around the value you're substituting in. So here we have minus Q, which is 4. So instead of just putting 4, we're going to put in parentheses 4 times R, which is negative 7. Again, in parentheses. And don't forget this final parenthesis there. Okay, so now we have a purely numerical expression in which we can use our order of operations and refreshment of exponential notation to evaluate. So what do? We begin first within grouping symbols because there are no fraction bars. So parentheses, so we're going to work within this area first. we have 10 minus 4 times 7. We do multiplication before subtraction. So 4 times negative 7 is going to be a negative number. Use parentheses. 28. Let's bring everything else down. All right, now we're still working within these parentheses. Now maybe you can notice here why the parentheses are important. We have 10 minus a negative 28. So a 10, if we're thinking on the number line, if we're at 10, and we're going to subtract a negative 28, this is addition. And again, if you're a little bit rusty or unfamiliar with adding and subtracting and multiplying negative numbers, it'd probably be a good time to review that, as we won't be doing that within this course. But 10 minus negative 28 is a positive 38. Bring everything else down. All right. No more grouping symbols to deal with. What do we have next? Exponents. So we won't write this out as 2 times 2 times 2. Do you remember what that product was? Yes, 2 to the third is 8. So we'll simply evaluate that. Using our parentheses. Now I'm going to drop the parentheses on here now. You certainly don't have to. All right. Now we have multiplication and addition. We do multiplication first. A negative 3 times 8 is negative 24 plus 38. One item left to do. A negative 24 plus a 38 will essentially be a 38 minus a 24, which is 14. All right, so given these values, this expression yields the quantity or the number 14. We change these variables, and of course, our final answer will be different. That review was fun and brought back some good memories, hopefully. If this is the first time you've been exposed to order of operations and exponential notation, please know there's a lot more that we could say, and we could take it a lot slower to kind of catch you up. But I think the homework will allow you to at least work through those steps and become familiar with these. So I'll see you next time as we work through the homework solutions together, and then we will rejoin our conversation back regarding real numbers, and specifically the real number line, as we'll be looking at distance on the real number line and absolute value. See you next time. Bye.
Thank you for learning with the Fosters. This is a friendly reminder. Remember that these courses are not for free. For information of the cost of the lessons and how to pay, please visit our website. Thank you so much for being with us.